Hey there, tech enthusiasts! Today, we're diving into the fascinating world of neural networks and deep learning. So, let's get started. Neural networks are essentially a set of algorithms that attempt to mimic the human brain. They're designed to learn and adapt, just like our brains do. By analyzing vast amounts of data, neural networks can recognize patterns and make predictions. Now, let's talk about deep learning. It's a subset of machine learning that uses neural networks to learn from data. Deep learning algorithms can process large amounts of unstructured data, such as images, videos, and text, and make predictions based on that data. How neural networks work and what is deep learning? Introduction. In recent years, artificial intelligence (AI) and machine learning (ML) have become pivotal fields driving innovation in industries ranging from healthcare to finance and entertainment. At the heart of these advancements lies a powerful technique known as neural networks, a core element of deep learning. In this article, we will explore how neural networks function, how they are trained, and how deep learning, a subset of machine learning, is transforming technology and industries globally. What are neural networks? Neural networks are computational models inspired by the human brain's structure and functioning. They are designed to recognize patterns, classify data, and perform a wide range of tasks, from image recognition to natural language processing. A neural network consists of layers of nodes, known as neurons, which are interconnected by weights and biases. These networks are designed to imitate the way biological neurons transmit information. At its simplest, a neural network works by receiving input data, processing it through multiple layers of neurons, and producing an output. The output could be anything from a prediction, for example, stock market prices, to a classification, for example, whether an image contains a cat or a dog. Each layer in the network performs specific mathematical operations, with the ultimate goal of transforming the input data into a desired output. The structure of neural networks. Neural networks consist of several key components. Neurons. Nodes. These are the fundamental units of a neural network. Each neuron receives input, processes it, and passes the result to the next layer of neurons. A neuron's output is determined by an activation function, which determines whether it should pass its signal forward. Layers. Input layer. This is the first layer of the network that receives the raw input data. Hidden layers. These are layers that lie between the input and output layers. Each hidden layer performs specific operations on the data, such as feature extraction or transformation. A deep neural network may have multiple hidden layers, which is where the term deep learning comes from. Output layer. This layer produces the final result, such as a classification label or prediction. Weights and biases. Each connection between neurons has an associated weight, and each neuron has a bias. The weights control the strength of the signal that passes between neurons, while biases help shift the activation function to better match the desired outcome. Activation functions. Activation functions introduce nonlinearity into the network, allowing it to learn complex patterns. Common activation functions include ReLU, rectified linear unit, sigmoid, and tan. These functions help the network make decisions and output values in a range suitable for the task at hand. How neural networks learn. The training process. Neural networks learn from data through a process called training. During training, the network is fed with labeled data input-output pairs, and it adjusts its internal parameters, weights, and biases to minimize the difference between its predictions and the actual output. The process of training a neural network involves the following steps. Forward propagation. The input data is passed through the network, from the input layer to the output layer. At each neuron, the weighted sum of inputs is calculated, and the activation function determines the neuron's output. This process continues through all the layers, ultimately producing a prediction. Loss function. The network's output is compared to the true label or actual value, and a loss function calculates the difference between the predicted output and the true value. This difference is called loss, and the goal is to minimize this loss during training. Backpropagation. Backpropagation is a technique used to optimize the weights and biases of the network. It works by calculating the gradient of the loss function with respect to each weight in the network, using a method called gradient descent. The gradients indicate the direction in which the weights should be adjusted to minimize the loss. The weights are then updated accordingly. Epochs. Training is typically done over multiple iterations, known as epochs. Each epoch involves passing the entire dataset through the network, performing forward propagation, calculating loss, and updating weights via backpropagation. The process continues until the network's performance on the task reaches an acceptable level. Deep learning, a subset of machine learning. Deep learning refers to a subset of machine learning that focuses on neural networks with many hidden layers known as deep neural networks. Deep learning models are able to automatically learn hierarchical representations of data, making them highly effective for tasks like image and speech recognition, language translation, and even playing complex games. The term deep in deep learning refers to the multiple layers in the network. While traditional machine learning models might use shallow networks, one or two hidden layers, deep learning networks can contain hundreds or even thousands of layers, enabling them to learn complex, high-level features from large datasets. Key features of deep learning. Representation learning. One of the key benefits of deep learning is its ability to automatically learn useful features from raw data. For example, a deep neural network trained on images can learn to detect edges, textures, and objects without needing explicit programming. Traditional machine learning, on the other hand, often requires handcrafted features. Scalability. Deep learning algorithms excel in tasks that involve large amounts of data. They can scale well with increased data, meaning they improve in performance as more data becomes available. This is why deep learning has become a dominant force in fields such as computer vision, natural language processing, and speech recognition. End-to-end learning. Deep learning models often work in an end-to-end fashion, meaning they can take raw input, for example, pixels of an image, and produce an output, for example, a label for the object in the image, without needing manual feature engineering or intermediate steps. This reduces the need for domain-specific knowledge and allows the model to learn directly from data. Applications of neural networks and deep learning. Neural networks and deep learning have revolutionized numerous industries. Here are some of the most prominent applications: image and video recognition. Convolutional neural networks (CNNs), a specific type of neural network, are widely used for image recognition. These networks are highly effective at identifying objects, faces, and even emotions in images and videos. Deep learning has made possible technologies like facial recognition, self-driving cars, and automated medical imaging analysis. Natural language processing (NLP). Deep learning techniques have significantly advanced NLP tasks such as language translation, sentiment analysis, and text generation. Models like OpenAI's GPT series and Google's BERT have set new benchmarks in understanding and generating human language. Healthcare. In healthcare, deep learning is used for tasks such as medical image analysis, detecting tumors in X-rays, MRI scans, etc., drug discovery, and personalized treatment plans. Neural networks help in identifying patterns in medical data that may not be immediately obvious to human doctors. Finance. Neural networks are used to predict stock prices, detect fraudulent activities, and optimize trading strategies. They analyze vast amounts of financial data to uncover patterns and trends that might otherwise go unnoticed. Gaming. Deep reinforcement learning, a subset of deep learning, has been used to train AI agents that can play and master complex games like Go, chess, and even video games like Dota 2 and StarCraft 2. The ability to learn from experience and improve over time has made deep learning a key tool in gaming AI. Challenges and limitations of neural networks and deep learning. While deep learning has shown remarkable success, it is not without its challenges. Data requirements. Deep learning models often require large amounts of labeled data to train effectively. In domains where data is scarce or expensive to label, this can be a significant barrier. Computational power. Training deep learning models, especially large ones, requires considerable computational resources. Powerful GPUs or TPUs are often needed, which can be costly. Interpretability. Deep neural networks are often referred to as black boxes because their internal workings are not easily interpretable. This lack of transparency can be problematic in fields where understanding how a model makes decisions is crucial, such as in healthcare or finance. Overfitting. Deep learning models are prone to overfitting, especially when the training data is limited. Overfitting occurs when the model becomes too specialized in the training data, making it perform poorly on unseen data. Conclusion: neural networks and deep learning represent some of the most powerful tools in artificial intelligence today. By mimicking the structure and function of the human brain, neural networks are able to process vast amounts of data, recognize complex patterns, and learn to perform tasks with remarkable accuracy. As deep learning continues to evolve, its potential to revolutionize industries like healthcare, finance, and entertainment is immense. However, challenges such as data requirements, computational costs, and interpretability still remain, but with ongoing research and development, the future of neural networks and deep learning looks promising. So, there you have it, a quick introduction to how neural networks work and what deep learning is all about. If you enjoyed this video, please give it a thumbs up and don't forget to subscribe for more tech insights. Thanks for watching, and stay curious.